100,000 cycles, 400 watt-hours per kilogram. This pack charges from 0 to full in as low as 5 minutes.
Solid-state compression pressure around 10 megapascals. Peak humanoid robot discharge currents exceeding 120 amps. Core battery temperatures potentially surpassing 150 degrees Celsius. Estimated cost near $650 per kilowatt-hour. These are the numbers Donut Lab uses to argue that its solid-state battery is ready for humanoid robots in 2026. And paradoxically, these same numbers expose why it is not. The claim of 100,000 charge cycles is the most seductive. On paper, it suggests a battery that outlives the robot itself, eliminating replacement costs and enabling continuous operation for decades. But the critical question is not how many cycles a battery survives, it is under what conditions. That figure is achieved under laboratory constraints. A low, steady discharge rate around 0.5 C, constant temperature near 25 degrees Celsius, no vibration, no mechanical shock. This environment has nothing in common with a real humanoid robot. Consider a practical example. A 50-kilogram humanoid, such as Unitree G1 or Optimus-class platforms, must constantly perform micro-adjustments to maintain balance. Each corrective movement sends sharp current spikes through the power system. When the robot transitions from standing to stepping, or recovers from a stumble, joint motors can demand instantaneous currents jumping from near zero to over 100 to 120 amps in milliseconds. These bursts are not anomalies. They are fundamental to legged locomotion. In a solid-state battery using a ceramic electrolyte, these current spikes translate directly into electrochemical stress. Ceramic materials conduct ions well, but are inherently brittle. Repeated high-rate pulses generate microfractures within the electrolyte and at electrode interfaces. In lab tests under gentle cycling, these cracks never form. Inside a robot, they accumulate rapidly. Modeling and early field data suggest degradation accelerates by an order of magnitude or more. Instead of 100,000 cycles, realistic lifetimes collapse into the range of 3,000 to 4,000 cycles, roughly comparable to high-end lithium-ion packs. At that point, the headline number becomes irrelevant. If real-world longevity is similar to lithium-ion, what problem has truly been solved? Energy density is the second illusion. Donut Lab advertises 400 watt-hours per kilogram, a figure that dwarfs the approximately 260 to 280 watt-hours per kilogram achieved by the best lithium-ion cells in 2026. But robots do not use naked cells. They use battery packs. Solid-state batteries require continuous mechanical compression, around 8 to 12 megapascals, to maintain contact between layers and prevent delamination. This necessitates heavy steel frames, spring mechanisms, reinforcement plates, and protective housings. The result is a dramatic penalty in volumetric density. While the cell itself may be light, the complete pack becomes bulky. Multiple analyses show solid-state packs occupying roughly 1.4 to 1.6 times the volume of a liquid electrolyte pack with the same usable energy. In a humanoid robot, volume matters more than mass. The torso is not an empty box. It is tightly packed with actuators, wiring, compute modules, and cooling channels. Imagine placing a physically larger battery deeper into the chest cavity. The center of mass shifts outward from the robot's rotational axis. This increases the moment of inertia, forcing motors to work harder during every step, turn, or recovery maneuver. Energy savings at the cell level are consumed, and often exceeded, by increased mechanical effort. The robot becomes less efficient, not more. So the question arises, what is the value of high gravimetric density if volumetric constraints negate it entirely? Fast charging is the third pillar of Donut Lab's narrative, and arguably the most misleading. Charging a 4 kilowatt-hour battery in 5 minutes requires nearly 48 kilowatts of power. Even assuming excellent ionic conductivity and low internal resistance, basic thermodynamics cannot be cheated. High current density produces heat. In electric vehicles, this heat is managed by large liquid cooling systems, pumps, radiators, and ample airflow. A humanoid robot has none of these luxuries. Its torso is compact, sealed, and already thermally stressed by processors, motor controllers, and actuators. There is no room for a vehicle-grade liquid cooling loop. As charging begins, temperature in the battery core can spike rapidly. Simulations show peak temperatures exceeding 140 to 150 degrees Celsius under aggressive fast charge profiles. At those temperatures, electronics protection systems will intervene. The robot will throttle charging or shut down entirely to avoid damage. Ironically, the promised 5-minute recharge becomes unusable in practice. Even if charging completes, the robot must wait additional time for thermal stabilization before operating safely. In effect, fast charging introduces a paradox. The faster you charge, the longer you wait before the robot can move again. Picture a humanoid slipping on a hard surface and falling sideways. The impact sends shock waves through the chassis. A lithium-ion pack may deform but continue functioning. A ceramic-based solid-state pack risks internal cracking, leading to sudden capacity loss or permanent failure. Over time, even normal walking on concrete introduces high-frequency vibrations that degrade the electrolyte. Placing such a battery near motors, which themselves generate heat, further accelerates aging. The battery ends up living in the harshest possible location. Then comes the economic reality. Solid-state manufacturing requires ultra-clean vacuum environments, micron-level layer control, and complex stacking processes. Yield rates remain poor, often below 50%. Capital expenditure is estimated at nearly 10 times that of lithium-ion production lines. All inefficiencies are passed downstream. At approximately $600 to $650 per kilowatt-hour, these batteries cost 8 times more than advanced lithium-ion or improved 4680 style cells. For commercial humanoid robots, cost is not a footnote. Robots are expected to operate in factories, warehouses, and service environments where margins are thin. A battery that is expensive, fragile, and difficult to service will not be adopted, regardless of how impressive its slide deck metrics appear. None of this means Donut Labs' technology is useless. The mistake is assuming universality. Solid-state batteries like this may find strong applications in stationary robots, fixed industrial systems, backup energy modules, or specialized drones with stable load profiles and active cooling. So the closing question is unavoidable. Are you evaluating a battery for real robots operating today, or buying into a carefully framed vision meant for a decade from now?